And, we've all been in classes of about, 25, 30, 35 people growing up in school. How often was there, a couple of kids that had the same birthday? So there are a couple different ways that we could go about trying to calculate this. And we're actually going to. So hopefully have your calculators or Excel around because you're going to be crunching some numbers. But we're actually going to find this probability to technically as many decimals of accuracy as you want. So we'll at least have, tenths and hundreds of percents. But calculating it directly is actually really difficult. So if we picked, say, a particular baby and tried to figure out, okay, what's the probability of that baby matching up with that baby, plus the probability of that baby matching up with that baby, plus the probability of that baby matching up with this baby, and did that for every other baby, we would then have to go to the next baby and say, okay, what's the probability of it matching up? And we'd have to remove all the cases where this baby was checked. It's a pain. It's possible to do, but it's a pain to do one at a time. What's much easier to do is to change the question. It's a very common thing to do in probability. We want to know what's the probability that at least two babies have the same birthday, and I want to look at our question's complement. Now, the complement in statistics, probability, in mathematics, the complement of something is the other part. It's the not our question. It's almost, think of it as the reverse of our question. So if we're being asked what's the probability that at least two babies have the same birthday, the complement of that is the probability that none of them have the same birthday. Oops. Birthday. If we knew the probability that none of them had the same birthday, we could subtract that from 1, subtract that from 100%, and we'd have the probability that one or more have the same birthday. So instead of having to figure out the probability that these two match up, that those two match up, that those two match up, if we find the probability that none of them match up, everything else has to be some matching. And as long as we have some matching, this situation is satisfied. Does that seem reasonable? Okay. So let's do that. That's the plan. So we got 23 babies. So baby number 1. What is the probability that baby number 1 has a birthday? It's a weird question. Well, 100%, right? Baby 1 has a birthday because it's baby 1. So baby 1 has a birthday. So it's boring baby 1. Chance of baby 1 having a birthday, 100%. Starts to get more interesting when we look at baby 2. What's the chance that baby 2's birthday matches baby 1? Or for our question, that doesn't match? How many days could baby 1 be born so that there's no matching? Of the 365 possible days that this baby could have been born, baby 1 could have been born on any of those 365 days and it wouldn't match because there's no other baby to match with. So the first baby could be born anytime. The second baby there are only 364 days left to avoid a match. Every day other than baby one's birthday. Does that seem reasonable? So baby two's likelihood of not being a match, remember that's our goal now, is no matches. There are 364 out of the 365. What about baby three? How many days are left for it to be born with no matches? Gonna make you guys tell me this one. So baby one has been born. Baby two has been born on one of the 364 days that doesn't match baby one. For no matches, baby three has to not be born on either of these two birthdays. So how many days does it have left? Nick? Yeah, 363 out of the 365 days. So all of these probabilities are pretty near to being 1. So of these three babies, almost 100% chance that each of them will be born on completely different days. Almost 100% chance that they won't match means almost a 0% chance of them all matching. So that's starting to look like our unlikelies. But how many babies do we have to go? 20 babies to go. Oops. Out of my way. Let me just move that over here. So we're going to keep doing this for a while. Baby 4 is born on one of the 362 out of 365 days. Baby 5, the probability that its birth date doesn't match any of the ones before, 361 out of 365. And we could keep doing this all the way until we got to baby 23. By the time baby 23 is born, how many birthdays would be left? I'll give you a moment to find that value. Out of the 365 days of the year, how many spaces, how many days could baby 23 be born in so that it doesn't match any of the others? 360 out of 365, baby 6. Now 342, almost 342, I think, is actually baby 24. Sorry. Notice baby 1 is all 365. Baby 2, we subtracted 1 from this list. Baby 3, we subtracted 2. Baby 4, we subtracted 3. We're subtracting 1 less every time. So of the 265, baby 23, we're actually only subtracting 22 birthdays because there are only 22 babies below it. So that would be, what, 343. Babies below it. baby 22 would be 344 out of the 365, and so on. Does that seem reasonable so far? Good. So if we wanted to figure out the probability of all of this occurring, I mean, baby 23, if we wanted to figure out, okay, once you have all the first 22 of the babies, the chances that that next baby doesn't have a birthday that matches any of those is 343 out of 365. That's still near, 90% or so. So each one of these probabilities is fairly small. Well, it's not small. Each one of these probabilities is fairly near 100%. So all of these individual things are fairly likely. But we want to look at what happens when we bring them all together. So if we have to have all of these things happen, what did we do with the probability when this had to happen and that had to happen and this has to happen and this has to happen? What was our operation when we said and with probabilities?
Multiply.
Multiply. So we're going to take that, multiply by 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 that, and we're going to multiply these things together all the way down. So what we would like to do is take 365, multiply by 364, multiply by 363, multiply by 362, multiply, and keep multiplying until we get to 343, and then divide that by 365, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 23 times. Now, if you're nervous about typing all of that into something like your calculator, you certainly could do that. You could type that in, all 23 of those numbers multiplied together. That actually wouldn't be that bad. But this is going to become something we're going to do with larger and larger number sets, not with, babies in these problems. But having to multiply out a lot of descending numbers like this is actually really common in probability and statistics, because of this idea that we first have, this many choices and then one less and then one less and one less. Every time we make a choice, the choices remaining to us go down by one. So there is a very common tool in numbers, technically in number theory, that we use when we've got this kind of scenario, when we have a product of descending numbers. Some of you may have seen it before, some of you may not have seen it before, but I want to take a minute and talk about it. Anybody seen it before and know what I'm going to talk about here? So, little side note into a mathematical tool we're going to need in chapter 6. And that is on factorials. Now, I'm not putting an exclamation mark here because I'm that excited about factorials. Factorials all are exciting, don't get me wrong. But the exclamation point is actually the symbol we use for factorial. So, for example, if we have 5 factorial, that is how we would read that. That is 5 factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. It's the product of every counting number from the number given down to 1. So 5 times 4 times 3 times 2 times 1 is what, 120. 20 times 6, yeah, 120. So that would make 4 factorial would be 4 times 3 times 2 times 1, which is what, 24? Yeah. 3 factorial, 3 times 2 times 1 is 6. 2 factorial, 2 times 1, 2 times 1, sorry, is 2. 1 factorial might seem a little bit weird. 1 factorial is just 1 times nothing else, so it's also 1. 0 factorial is even weirder. 0 factorial will come up from time to time, and there is no counting number less than 0 that's greater than 1. 0 factorial is just defined as, if you've never seen the triple equal sign, it means defined as. 0 factorial is simply defined as 1. Essentially, 0 factorial isn't there, and you've always got 1 times anything. So if you ever see a 0 factorial, just get rid of it, replace it with the 1 that's in front of it. So that's just a definition for factorials. So we will see that happen, but don't worry about that. So factorials allow us to multiply numbers in this kind of descending order here. So the 365, 364, 363, 362, if we want to multiply all those together using a 365 factorial is going to be handy. Not quite enough, but handy. So that 365 factorial is going to be the 365, the 364, the 363, 362, 361. The problem is 365 factorial is going to go all the way down to 1, and we want it to stop at 343. So we need a way to get factorials to stop, and it's actually really nice. Let's say we imagine we have 8 factorial and we divide 8 factorial by 5 factorial. Now we could calculate what 8 factorial is. Your calculators actually have a factorial button. They literally have an exclamation point button in them. It's under your math sub menu under probability. Or you could go to, on the net and just into, Bing or Google or whatnot, hit 8 exclamation point, and it'll likely pop up with that factorial value. But I want to look at what's mathematically actually happening here. If we look at 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the definition, again, of factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So notice what happens with the 5, 4, 3, 2, 1s in both cases. The 5, 4, 3, 2, 1 on the bottom is going to cancel with the 5, 4, 3, 2, 1 on top and just leave us with the 8, 7, 6. We essentially got the 5 and down to go away by dividing by all the pieces we wanted to have disappear. So one of the nice ways to write a statement like this is we take the 365 factorial. That's going to be all of the values from 365 down multiplied together. But I don't want the numbers from 342 down. So I don't want anything after 343. So if we put 342 factorial in the denominator, then the 342, the 341, the 340 that are up here in the factorial are canceling with the ones in the denominator, and they're going away. So this gives us a very nice way to write a string of products that we can type very quickly, as long as we know that factorial tool and that factorial button. We still do need that denominator to have the 365 to the 23rd power. But it saves us a lot of writing, and when we try to put it into a piece of technology, it saves us a lot of typing. Now, we'll use that tool in some particular ways in chapter 6, as I said, so make sure you're happy-ish with that idea. We'll talk more about it as we go along, but have any of you seen that factorial before? If you've seen it before, make a little note in the comments while I load up my calculator. If you've seen that factorial tool before, anybody? It's not unusual for nobody to have at this point in your mathematical careers, but it does come up a lot in probability. And hopefully you can see why. It's the idea of that, you know, every time we do a step, we remove one option. So, you know, like even things like we're trying to figure out how many different ways we can put, you know, 6 things into 8 boxes. Well, you first have 8 choices. Once you make that first choice, you now have 7 choices, then 6 choices, then 5 choices, then 4 choices, then 3, then 2, then 1 choice. So it's very common in counting theory, in probability, and in statistics. So in our calculators, as I said, it is in your calculator tools. We want that numerator, 365 factorial. So 365, and we need that factorial button. So I'm going to go to my math submenu here, math, and slide over to probability at the end, PRB. And notice that number 4 is that exclamation point. That is 365 factorial. And if we hit enter, it'll try to multiply that out. That is a gigantic number, by the way. I'm not even sure the calculator will do it. I want to find out. Nope, it goes, I cannot calculate a number that big. But that's okay, because we're going to make it smaller when we divide, because we're going to divide out 342 of those things it's trying to multiply together. So divide by, I do want parentheses down here, because we have to divide by this whole thing. So we're going to divide by the 342 factorial, in math, probability, and then factorial. But that's got to be multiplied by the 365 raised to the 23rd power. Now, there are a fair number of big numbers going on in this problem. That 365, oh, sorry, that 365 factorial was too big of a number for your calculator to handle. The 365 to the 23rd power, that's even larger. So these numbers are huge. But if we have it evaluate all of them all at once here, oh, it still panics. I was hoping it wouldn't panic. Anybody's calculator not panic? I'm going to have to use Excel to do it. Here's panicked, Olivia. And again, these numbers are gigantic. Even looking at, say, oops, I don't want that. Clear. Even looking at, say, 20 factorial, 20 math. 20 factorial is 2.4 times 10 to the 18th. That's a million. That's 2.4 million, million, million. And that's at 23 factorial. So it shouldn't be too much of a surprise that 365 factorial was bigger than this thing could even try to calculate. So we're going to need a bigger tool. So we're going to grab the bigger tool. Let's grab Excel. Hope Excel works for this. Luckily, if not, I can just tell you what it equals because I know about what it equals. But what's it going to do with 365 factorial? This nice thing about Excel, you can just use the exclamation button. Now, Excel does 125,000 decimal places, so it should be able to handle that. No.
Did it not work?
Oh, it doesn't like my formula. Does it not use the exclamation point? No, it uses fact. That's weird. It's a different addition than I normally use. Oh, yeah, okay. So it uses fact. So we would need a factorial 365 divided by, now it's easier to look at it typed up here, parentheses, factorial 342 times 365 to the 23rd power, and cross our fingers that that's not going to blow Excel with its giant numbers. Oh, no, it'll be okay. It'll be okay. It'll be okay. It'll be okay. No, it won't be okay. Oh, no. Ever think you should have tested something out before you did it? No, the numbers are too big even for Excel. Okay. So it's actually interesting to see that happen. So what we would need to calculate this number is a supercomputer, because those numbers are giant. But the nice thing is, if we did have such a computer and it cranked out all those numbers, or if we did it all by hand, that's not going to happen by hand, by the way. That would take you decades, if not lifetimes, to calculate out by hand. But the surprising result is that this equals roughly, for 23 babies, it equals roughly 49.3. Well, technically it's 0.493. And hopefully it's not too surprising that this number is less than 1. You got all these 23 365s down here. So that's going to make this, a fairly large denominator. You've got these numerators up here that are all a little bit less than that. There are 23 of them. So there's a smaller denominator than numerator. So that 49.3 hopefully doesn't seem too crazy. And if we do our 1 minus our 0.493, we do get about 50.7, well, 0.507, or 50.7%. So whoever said it was number 5 and that it's about 50-50 and didn't sneak off to then do number 2, you had the right answer, Grace. Is correct. The reason, by the way, I happen to know what that answer is because 23 is the number of babies that makes it as close to 50-50 as possible. I'm glad I didn't pick some other number. No. But it can be quite surprising that at 23 babies, it's a 50-50 shot whether you're going to have two of them that have the same 365 out of 365 birthdays. What might be even more surprising, by the way, is if you go to 75 babies, it's almost 100% chance. It's at 75 babies, it's 99.97% chance if you have 75 babies. So if you have 75 people in a room, there's a virtually 100% chance two of them will have the same birthday. And that just should seem crazy. Maybe should, maybe shouldn't. Not to Grace, which is good because it's not crazy. Now, why is this an important problem? Well, not only because it's, kind of neat and it's, brings up, it works against our expectations, but this is one of the ways that computer hackers use to get at our information. So instead of having birthdays match up, say we're trying to have passcodes match up or computer ID protocols match up. Okay, there are often a few more than 365 choices in things like passkey protocols and whatnot. So those usually quite a lot more than 365 of them. But if you send out a comparatively small number of checks out into a system of just even a blank distribution of Wi-Fi networks, and you throw out bits of code, what's the probability that those bits of codes will match up? It's surprisingly high. Just like trying to get, how many kids do we need for the birthdays to match up? How many signals do we have to send out for their IDs to match up? Is surprisingly small. One of the reasons that our internet security protocols have to be as tight as they are, and why you need those, I think modern ones are 24-digit stream of 32 hexadecimal based numbers. The number of possibilities in the coding is in the trillions of trillions. Why? Why does it have to be that hard to crack? Because 23 babies match up. So it's just an interesting problem in probability that allows us to talk about a couple of things. One, this idea of multiplying. I know we talked about that last time, but whenever we have those ands, we do have to multiply. Allows us to talk about the idea of factorials. And even with this, it gave us a nice chance to see some of these numbers are going to get gigantic when we start working on probabilities. Anytime you have something happening over and over again, even 23 times here, those numbers get massive very, very, very quickly. And we're going to need a way to control those massive numbers. And factorials will help us deal with those massive numbers. But as we can see, sometimes even our modern computer balks at it a bit. That's one of the reasons they have those big supercomputers, so they can compute massive probabilities like this. So questions about this question. It's also just kind of a neat, I think, kind of a neat question.
I don't know. I'm still trying to process it because there's so many numbers.
It is. And it's so many numbers and so many gigantic numbers, if we actually looked at those numbers. Now, where are we going to use this factorial stuff? Well, one of the things that we're going to do is look at how many ways, I'm just going to use things can be organized. And why organized? Well, organizing data, organizing information is one of the things that we're working on here. So if I have, say, 1, 2, 3, 4, 5 different objects here, I've got an A, B, C, D, and E. And I want to arrange those 5 objects in 1, 2, 3, 4, 5 different baskets. One of the parts of our questions is going to be, how many different ways can I arrange these 5 things in those 5 baskets? And we could just try to count them if you wanted to. You know, we could put the A there, we could put the B there, we could put the C there, we could put the D there, and the E there. That's one choice. We could also put the B there, the A there, the C way over there, the D there, the E there. That's 2 choices. How long do you want to spend figuring out different choices for this? Put the B there, the C there, the A there, the D there, the E there. That's 3 different choices. This would go on for a long time. Fair? So we don't want to have to count up opportunities that way. What we're going to do instead, how many different letters can go in this first box? Got a nice 5 from Allie there. Yeah, there are 5 different choices for that box. After you select one of those letters, whatever it is, after you select one of those letters for the first box, how many letters can go in the second box? The 4 remaining letters. Yeah. How many letters can go in the third box? How many letters can go in the fourth box? How many letters are left to go in the last box? So how many different ways can we organize these 5 things in those 5 boxes? 5 factorial ways, which is 120. We'd have been counting 120 different. What if instead of 5 letters and 5 boxes, we wanted to count up given all 24 letters. So given all of our letters, A through Z, how many 5-letter words are there? Now, I have words in quotes there because it doesn't have to actually be a word. Just any string of 5 letters is a 5-letter word. So A, I, that's a word, according to this. So how many 5-letter patterns or codes could we have? Well, how many letters can go in the first box? I heard Allie say 24. How many letters can go in the second box? 23. Then 22 in the third box, 21 in the fourth box, and there are 20 different letters that can go in the last box. So how many different ways could we arrange that? Well, I want 24 multiplied downward, That's going to give us 24 times 22 times 23 times 22 times 21 times 20. But it's also going to give us times 19 times 18 times 17 and so on. We want to get rid of the 19, 18, 17, 16, and so on. So we need those to cancel out. So we're going to divide that by 19 factorial. You'll often see this written, by the way, as n over n minus x. The number of ways over the number of ways minus how many boxes we filled. So 24 over 24 minus 5. 24 over 24 minus 5 factorials. Now, I am curious if the calculator will handle that. It let me down before. I know it can do 20 factorial. It should be able to handle this, but we'll see. I know Excel will, so I'm not too worried. So 24 math probability factorial. So 24 factorial divided by 19 factorial. Okay. There are 5.1 million different ways. 5.1 million different 5-letter combinations. So if you have say a password that's got to be 5 letters and you want to pick it at random, what's the probability that you will choose the right password? 1 out of the 5.1 million. Those would be your odds or your probability of randomly choosing the right password with 5 letters. Well, we're going to be talking about probabilities, so we're going to need to be talking about counts. And factorials are a very common tool for using to find counts. As we get into particularly 6.2. So you guys said it was your first time seeing it, or didn't say anything about having seen it before. Thoughts about this tool? Is it a neat tool, factorials? I got one yes and one no. One of the nice things about them, though, is you often don't deal with the actual values. You let the tech do it. And yeah, if the numbers get big enough, the tech starts to slow way down. But that's actually one of the interesting things about our modern world. There are so many things in the technology that we have that are only possible because of our ability to calculate some of these extreme value sets. And the programming required and the math required to be able to calculate these probabilities so we can build things that don't blow up is often based on crunching some incredibly large numbers to find patterns. You can make an entire career out of it if you decide you want to. And get paid oodles by the government for cybersecurity and stuff like that. It's great. Okay. So next time I want to look fairly quickly, probably spend about half of our time in 6.1. 6.1 is with all this background, 6.1 should go very, very quickly. and then jump into 6.2 and start talking about binomial probability distributions. So that's the plan. You guys have any questions?
No, thank you so much.
Sure. Nick or Grace or Tessa or Micah or Leslie, you guys have been fairly quiet today. You guys all doing good? Nick's good. Grace, you're learning to trust your intuition. Okay, looks like you guys are good. I got that. I did. Thank you. Okay. Well, I'll see you guys tomorrow then. And if there's anything you need between now and then, let me know.
Okay, thank you. Bye.
Bye-bye.